In this video, we'll talk about a second way to think about substitution method problems that can make it easier to figure out how to actually proceed through these problems. So the expression we had was something of the following form. And this is sort of how I want to think about these problems. The point is, if I can make a substitution into my integral so that I plug in some u for this g of x, and then also change the differential to a du, then I can do this problem directly without worrying about making sure I match the formula exactly and everything works out nicely. So for these sorts of problems, what you want to do is pick your u and then compute du. So if I compute du, this is a differential we talked about previously. For u as a function of x given by g of x, then du is given by g prime of x times dx. So if I can pick an appropriate u where I can then find this du in my problem statement, say as this g of x dx up here, then I can just plug this in and I will get the next step of the problem. Right? If I plug in to an expression integral of f of g of x times g prime of x dx, if I set u to be this function g of x, then du is g prime of x times dx by the definition of differentials. Then if I just plug this into here and this into here, I just get integral of f of u du. And now hopefully if I've done my work right, this is nothing I can directly integrate. And by that I mean I have a rule for computing this integral on the right where I didn't have one for the integral on the left. And so this sort of aiming for setting u to be some function, finding du, and trying to plug them both in is also the substitution method, but gives us a different way of visualizing it that might be easier for processing through these problems. So pick u, compute du, and then substitute them in. So the substitution method, we're substituting things in, and this choice of letter for u is traditional. You can pick whatever letter you want, but u is used a lot, and this is why it's also something called u substitution. Let's look at some more examples. So integral of 3x squared cosine of x cubed dx. The way I want to solve this is again by our differential form here. So I'm going to set u to be the inner function of x cubed. Then du is 3x squared dx. And I see the 3x squared dx right here. So I can rewrite this integral now as the integral of cosine of u du that I can integrate to sine of u plus c, and then I can plug my u back in to get sine of x cubed plus c. That's the idea how this stuff usually works, and the answer will pop out like that. What about this one here? Integral of x plus 2 times x plus 4x plus 10 all to the fifth. Well, it looks like this whole thing to the fifth is kind of like an inside function. So just like for the chain rule, the inside function is usually a good place to start. Let's see what that gives me. So if I set u to be x squared plus 4x plus 10, I then get a du that is 2x plus 4 times dx. Now I don't see a 2x plus 4 here. There's an x plus 2, which is pretty close. How can I work that out? You can either try to make this x plus 2 here look like 2x plus 4 by multiplying and dividing by 2, or you can just solve out for dx in the equation over here and then plug that in and see what happens. So I can solve out for dx. dx is then du over 2x plus 4. And then I can plug u in and I can plug dx in and see what happens. In that case, I get the integral of x plus 2 times u to the fifth times du over 2x plus 4. And I realize that this here is 2 times x plus 2, and then the x plus 2's cancel. So I'm left with 1/2 integral of u to the fifth du, and now this I can integrate. So I get a 1/2 times 1/6 u to the sixth plus c. I can then plug my u back in to get my final answer of 1/12 x squared plus 4x plus 10 to the sixth plus c. And so the problems like that work out. You can either identify the du in your expression and plug it right in, or you can just solve out for dx and plug that in and see where that gets you towards solving the problem. And the important step in this whole process is picking the appropriate u, and that can be tricky depending on the situation. So in general, if you want to look for the u, you're looking for some sort of inside function. This method comes from the chain rule, which uses these outside-inside functions. So looking for an inside function should not be coming out of nowhere for this method. The other possible technique is to look for what a du might be based on what you have multiplying dx. For the situation, you always have that du is something times dx. If you've got a nice expression that might be a good du for something else in your problem, you could start by looking for the du and just sort of backward construct what your u should be and see if that works as well. One more example here, integral of x squared times x cubed plus 1 to the 8th times cosine of x cubed plus 1 to the 9th dx. So for this one, we're going to look for an inside function. And here, the inside function I see is this x cubed plus 1 to the 9th in here. So I'm going to set u to be x cubed plus 1 to the 9th. Then my du becomes a 9 x cubed plus 1 to the 8th times a 3x squared dx by the chain rule. Thankfully, I almost see that out front, since this is a 27 times x squared times x cubed plus 1 to the 8th dx. Here is my x cubed plus 1 to the 8th times x squared, I'm missing the 27. So when I plug that in, I will get a 1 over 27 integral of 27 x squared x cubed plus 1 to the 8th cosine of x cubed plus 1 to the 9th dx. I now have u and I have du. So this becomes a 1 over 27 integral of cosine of u du, which becomes sine of u, and so I get a 1 over 27 sine of x cubed plus 1 to the 9th plus c. Now for this one, if you pick the wrong u to start, you're not out of luck. Right, for this one, you could also start with u equals just x cubed plus 1, if that was like your inside function, because that's more inside. If you do that, your du is just 3x squared dx. So then my integral ends up being a 1/3 3x squared x cubed plus 1 to the 8th cosine of x cubed plus 1 to the 9th dx. I have u in here and du sitting out here, but this here is now also u. And so when I make this change, I will get 1/3 integral of u to the 8th cosine of u to the 9th du. And I can now make a second substitution, say setting v equal to u to the 9th, dv is 9u to the 8th du, and do that one, and I'll get to the answer at the end anyway. So even if you make the wrong substitution, doesn't quite get you all the way there, you can still do this method multiple times in a row. That'll eventually get you the same answer you're supposed to get to at the end. You'll eventually reach 1/27th sine of x cubed plus 1 to the 9th plus c. So that's the differential form approach to the substitution method, and ways that you can use it to help you work your way through these sorts of problems to get to these answers that require the substitution method.